Welcome to this week's Short Clip Friday podcast. Each Friday, I'll be posting 10 to 15 minute segments from previous podcasts. And the point here is just to bring you some of the highest yield topics from each podcast in order to kind of reinforce those topics. This clip is from the Isomers podcast and covers stereoisomers. Enjoy. So there's three different kinds of stereoisomers I'm going to talk about. I'm going to talk about enantiomers. I'm going to talk about diastereomers. No one knows how to say that word, diastereomers. We'll get into that. And then conformational isomers. All right, so in general, stereoisomers are isomers that have the same atomic connectivity, but differ in the spatial arrangement of atoms. So as I said a little bit earlier, geometric isomers or cis-trans isomers are technically stereoisomers. I like to pull them out because they're really important, but they are stereoisomers. However, when you typically think about a stereoisomer, you usually think about enantiomers and diastereomers. So let's get started with first talking about enantiomers. So these are stereoisomers that are non-superimposable mirror images of one another. The classic example here is your hands. So if you take your hands and you look at both of them, put them out in front of you, and you can see that they are mirror images, right? If you were to draw a plain line between both of them, one is just the mirror image of the other. However, if you took your right hand and now tried to lay it on top of your left hand, and what you have to do is you'd have to turn it palms up to make it fit. Well, now you try to do that, it's not the same object, right? Your right hand is not your left hand. They're non-superimposable mirror images. A more molecular example is D-glucose versus L-glucose. And if you look at a straight chain drawing of glucose, specifically of D-glucose versus L-glucose, you can see they only differ in the configuration at one carbon atom, which is like the carbon atom typically at the very bottom of the chain, depending on how you draw the chain. But again, these two molecules are non-superimposable mirror images of one another. On the other hand, diastereomers are stereoisomers that are not enantiomers. In other words, they are isomers that have the same atomic connectivity, but differ in their spatial arrangement of atoms, but are not non-superimposable mirror images of one another. And one common example of a diastereomer is what's known as an Epimer. And this is a type of isomer in which the isomers differ in the configuration only at one stereogenetic center, and all of the other stereocenters in the molecule are the same. And this is something like glucose compared to galactose, which again is easy to see if you're looking at the straight chain representation of glucose versus galactose. So again, diastereomers are simply stereoisomers that aren't enantiomers. That is, I can draw their mirror image, and then I can actually impose that mirror image back on the original molecule, and it's the same molecule. All right, so the last type of stereoisomer I want to talk about are called conformational isomers. And these are a little bit weirder than the others. But stereoisomers are produced by rotating about some single bond. And what you're doing is you're actually rotating a group of atoms that are connected to a stereocenter. And a stereocenter is an atom that has at least three different attachments that is able to form a stereocenter. So an example of a stereocenter would be like a carbon that's attached to a fluorine, hydrogen, another carbon, and a chlorine. That's obviously four different things, but if there was a double bond involved, this carbon could be attached to three different things and still be a stereoisomer. So I guess the rule should be that a stereocenter is some type of atom that's connected to either four different types of atoms or connected to three different things with a double bond. And so conformational isomers are typically shown with a Newman projection. You might remember like butane, which I think is one of the classic examples, drawn in a Newman projection. And as you rotate one of those substituent groups around, you get these different conformations and therefore different conformational isomers. And there's a few different conformations that you might want to know. The first is the Eclipsed Conformation. The second is the Gauche Conformation. And the third is the Anti-Conformation. In butane, the eclipsed conformation is when you have this methyl group, the CH3 group, that is in line with the other CH3 group on the opposite side of the molecule. The gauche is when you rotate that front substituent group by 60 degrees. So you have one methyl group kind of cockeyed to the other at about 60 degrees. And then the anti-conformation is when you have the methyl groups on opposite ends of the molecule, like one's pointing up, one's pointing down on opposite sides. And that is typically the lowest energy conformation of butane. And that's where butane tends to like to hang out because it's in that lowest energy state. So just to summarize those, enantiomers are stereoisomers that are non-superimposable mirror images. And then you have diastereomers, which are stereoisomers that are not enantiomers. Then you have conformational isomers, which are stereoisomers produced when you rotate a molecule around some single bond. All right, so I want to discuss a few important applications of stereoisomers that you might see on the MCAT. The first is a few terms related to stereoisomers you might see. The second is in identifying stereocenters. The third is in R and S naming, as well as relative versus absolute isomers. And then the last is in SN2 reactions. And then I'll add in a little bit about allulose versus sucralose versus glucose, which is just a non-MCAT interesting nutrition-related thing. So there's a few terms that you should know in reference to stereoisomers. The first is optically active. So what it means for a substance to be optically active is that it can actually rotate plane polarized light. And what type of molecules can do this? Well, chiral molecules can rotate plane polarized light. And now, of course, you're saying, okay, what is the definition of a chiral molecule? Well, a chiral molecule is simply a molecule that can have an enantiomer, i.e., it's a molecule that has a non-superimposable mirror image. So to quickly summarize that, in order for a compound to be optically active, it must be chiral and it must be an enantiomer. Another term you might see come up is mesocompound. And a mesocompound is a molecule that has multiple stereocenters that is superimposable on its mirror images, i.e., it is not non-superimposable. In other words, it's a molecule that has multiple stereocenters, so it appears to be optically active, but it's actually not. And why is it not? Well, it's because a mesocompound has an internal plane of symmetry. In other words, you can look at this mesocompound and you can draw a straight line through the molecule somewhere in it, and it will look exactly the same on each side of this line. So don't get fooled by a mesocompound, say you're given one. Don't be fooled into thinking that it is optically active because it's not. Instead, it's a mesocompound. The second application is in knowing how to identify stereocenters. And as I said earlier, a stereocenter is an atom that has at least 3 different attachments and is able to form a stereoisomer. Typically, this is going to be an atom connected to 4 different things or an atom connected to 3 different things with a double bond. And so you need to be able to look at this big, massive molecule and be able to pick out the stereocenters in the molecule and, either count them up. I've seen questions that say, how many stereocenters are in this molecule? And then it just gives you a molecule. So know how to do that. And my one piece of advice here would be to remember that hydrogens are typically not shown on molecular drawings. And so it's easy to forget to include a hydrogen. Like you might see an atom and you're like, oh, it's only connected to 3 different things. But then you realize, oh, hydrogens aren't drawn in on this drawing. So it actually is connected to 4 different things, and it is a stereocenter. So I recommend just practicing those types of questions if you are struggling with it. Another important application in terms of the stereocenters is calculating the number of stereoisomers a certain molecule can have. So again, let's say the MCAT shows you a compound, and then it says, for this compound, say drug X, how many stereoisomers are possible? Well, all you got to remember is that the number of possible stereoisomers is equal to 2 to the power of n, where N is the number of stereocenters. In other words, the number of stereoisomers you can have grows exponentially with the number of stereocenters that you have. The third application is in RS isomer naming, as well as relative versus absolute isomers. So there's a naming system for these stereoisomers, and that is naming them either R or S. And there's some Latin name, I don't really know how to pronounce it, so I'm not going to. But the rules for this naming system are very similar to the cis-trans naming. Essentially, you're going to assign priority to each of the groups that are attached to your stereocenter, and then you're going to rotate this molecule that you're looking at so that the lowest priority substituent is facing backwards, and then you're going to take the three substituents that are facing you, and you are going to draw a circle from the highest priority group to the lowest priority group that's facing you. This is going to be the second lowest priority overall, and that is going to determine whether this molecule is R or S. If the circle you drew is clockwise, then it's going to be R. If the circle you drew is counterclockwise, then it's going to be S. And for me, this is easy to remember because I just remember that if I want to turn right in a car, which way do I turn the steering wheel? I turn it clockwise, R. And I think this is another one of those things that you need to practice if you don't understand. Get a pen and paper out and just kind of help yourself understand this, understand how to do it. I wouldn't say it's super high yield, but definitely would not hurt to know the RS naming system. The other thing I wanted to talk about was the difference between absolute and relative configurations of stereoisomers. Essentially, the absolute configuration of a molecule is the precise arrangement of substituents at a stereocenter. So that is going to be the RS naming, where I could point at a stereocenter and you could say that's RS, and that doesn't change at all. However, for the relative configuration, we're looking at the position of atoms or groups in space in relation to another part of the molecule. So this is going to be the cis or the trans isomers, right? You're looking at the position of some substituent group in reference to another substituent group on the other side of the molecule. So you can think about relative configuration being cis-trans and absolute configuration being RS. The next thing I wanted to talk about was the relation of an SN2 reaction to stereoisomers. So an SN2 reaction is a nucleophilic substitution reaction, and it is a single-step reaction that results in an inversion of previous stereochemistry. So if you started off with an S molecule and that undergoes an SN2 reaction, you will now have an R molecule and vice versa. So if you start with an R, then you go to an S. So that's just something to keep in the back of your head as you're taking the MCAT. And before I go, I want to talk about one interesting case of stereoisomers in different sugars. And so obviously stereoisomers play a pretty big role in different sugars, right? As I was saying, glucose and galactose are two different diastereomers, whereas L-glucose and D-glucose are different enantiomers. The sugars I want to mention are allulose, sucralose, and glucose, which allulose and sucralose are two fairly common sugar substitutes. Allulose is a rare sugar that's found in nature, and they now invented this enzymatic process where they can create it in the lab. Sucralose, on the other hand, is completely lab created and is basically a chlorinated glucose and has chlorine added on. So obviously, sucralose is not an isomer of glucose. It has a whole nother atom, and it kind of has a weird aftertaste. And I'm not sure if that's because of this extra chlorine group. I don't really know. On the other hand, allulose, which is also known as D-piscose, is a diastereomer of fructose, which this is very similar to sucrose, which is a table sugar, right? Sucrose is just a disaccharide of fructose and glucose. So this diastereomer of fructose, which is allulose, is actually very similar to this table sugar. And so allulose tastes a lot like table sugar. It has a very similar consistency to table sugar, but it is a different sugar, right? It's a diastereomer, and we don't have the enzymes to actually metabolize allulose, which is kind of crazy to me, right? We have enzymes to metabolize fructose, glucose, plenty of other sugars, but just this one sugar that's a diastereomer of fructose, we don't have the enzyme. And I don't know why. It's probably because it's pretty rare in nature, so we didn't ever need to have that enzyme, evolutionarily speaking. But anyway, so we can't metabolize the sugar, so it just passes through us and we excrete it out, which, by the way, is pretty much the same thing that happens to sucralose, right? We don't have the enzymes to digest sucralose, so it just passes through us. So there's no caloric intake from these sugars, or at least very little intake of calories from these sugars. And very recently, in April of 2019, the FDA approved allulose to be taken off of the added sugar part of nutritional labels. So because of that, I assume that this substitute sweetener, or the sugar substitute, is going to get more and more popular, and we're going to start seeing it in more and more products.